Hello everyone. All right, it is time for us to work on, there we go, 6.2 and 6.3. So this should be rather quick because almost all of this is review, and it's going to hopefully be pretty easy for you guys. All right, so we're gonna go through the PowerPoint, and I do have a little bit I'll do on the notes at the end, but not very much. All right, we're back to energy diagrams again. And then talking about heat transfer and how heat transfers between two objects. So that's our focus for 6.2 and 3. So we get to kill two birds with one stone. So this is an energy diagram for an exothermic reaction. And by this point in time, I expect you to be able to know that because we've been talking about this. Remember that you can identify this and your reasoning, if you were to explain why, if you were doing a claim evidence reasoning, your reasoning to explain why or how you know that this is exothermic is, number one, the evidence is that your products are lower in energy than your reactants are. And so when you subtract products minus reactants, then that means that energy had to be released in order for the products to be at lower energy. And that products minus reactants is going to give you a negative delta H value, which goes along with the fact that energy, in order to get from here to here, energy had to be released or let go or exited the system, or however you want to think about it or word it, because that's what's really important. But the products are lower in energy than the reactants because the energy has been released. This is exothermic. Okay guys, when we hit stuff multiple times, that's a really good indicator that it's going to be on the AP exam, okay? And it's hit multiple times, not because I say so, but because AP says so. So I do whatever they say. So this is going to be really important to you. Endothermic, again, you take a look. Your products are in higher energy than the reactants are. So, I'm so sorry. So that means in order for the reactants, which are here, to be at this higher energy level, you have to put the energy into that system in order to make it happen. So energy went in, that makes it endothermic, all right? So that is, again, something you need to be able to instantly recognize and know right away. And many times on the AP exam, they may not tell you something's exothermic or endothermic. They may not give you a graph. They could just give you some cell or delta H value. And what you're really looking at is the sign. Is it positive or is it negative? Endothermic reactions are positive, exothermic reactions are negative. So make sure that you are very, very, very quick on recognizing that. Okay, so enthalpy reactions. So this looks like all kinds of crazy convoluted equation. It's what's on your formula sheet. So we're going to talk about it. It's not that bad. It's still just ultimately sorry, products minus reactants. But we call this delta H, it's the enthalpy of the reaction, the heat of the reaction. And you're like, well, enthalpy is H, right? And heat is supposed to be lowercase q. But for what we deal with in AP chemistry, delta H and Q are almost always the same thing. And it's really gotten to the point now where I feel like it's very rarely where it's not the same thing, and we'll talk about that when we get to it in a little while. Not today, but on a different day, about what's the difference and when are delta H and Q not the same thing. But typically, delta H and Q are the same, and you can interchange them in their formulas, okay? And we'll talk about that later. But the units on delta H are going to be kilojoules per mole of the reaction. It is imperative, listen to me, imperative that when you do your calculations, you have per mole. Now you don't have to put the Rx in for the reaction. Don't waste your time, but just per mole. Kilojoules per mole is essential. Your calculation is going to only give you kilojoules most of the time. If you're, well, depending on which way you're calculating delta H. But there are some ways that you calculate delta H. Like if you were doing from the energy diagram, if they had values on the y-axis, you are just having energy, which is kilojoules. And so mathematically, your units will come out to be kilojoules, but your answer absolutely has to be in kilojoules per mole or it will be marked wrong. Hear me. You do everything right, your math is right, all your signs are right, you've got kilojoules for your answer, and kilojoules is what works out in your algebra, like with your units. But if you don't put the per mole on the delta H, the AP will mark it wrong. And they're talking about per mole of this particular reaction, which is why they have the subscript RXN. However, that's not required, so, you don't have to put it. Now, this is basically the delta H of the reaction. Remember that little naught symbol there means that you're at standard conditions. Is equal to, all right, that means sum. So you sum up your enthalpy of formations. That should be a subscript F. It got a little bit wonky when it transferred over from a PowerPoint to a Google slide, so sorry. But delta H of formation at standard conditions of your products. So basically you have your H's for your products, okay? Enthalpies for the product. Minus the sum of the H's of formation at standard conditions for the reactants. Products minus reactants. If you have more than one product, you have to sum them up. If you have more than one reactant, you have to sum them up. So you have all your products together, all your reactants together, they're summed up, subtract them, and you'll get the delta H for the reaction, and that's it. And you'll write your answer in kilojoules per mole. Per mole. Okay, don't forget. The sign of delta H is really important, and sometimes that's the only indicator of if you have an exothermic or endothermic reaction, so you have to pay attention. Negatives are exothermic and positives are endothermic. It is super important, and that's that. So nothing else to really say about that. I've really hit it. We talked about this on the last video. For right now, in chapter 6, we're only focusing on these two, and this is a better representation of the equation that was on the last slide, because it's a screenshot, it didn't get all wonky with the formatting, but it's the same equation that we just looked at. So easy peasy in terms of calculations. We'll deal with those other equations later. So what is activation energy? We know this because we just did this in Unit 5, right? So activation energy is the amount of energy it requires in order for a reaction to start and get up over that hill, right? So the reaction can proceed to make or to continue to make the products. So activation energy is used to break either, oh, didn't mean to do that. There we go. It's used to either break bonds or intermolecular forces. So it just depends on what you're trying to separate from itself or from each other. So it could be intermolecular forces, like we talked about, splitting water molecules apart, like not breaking a water molecule, but two water molecules that are hydrogen bonded to each other. They will pull them apart, that intermolecular force, and also breaking bonds. Not the case in separation of water, so don't get that messed up. But the activation energy is energy used to either break bonds or separate molecules from one another, intermolecular forces. The energy that's released from this particular reaction comes from the formation of the new bonds and or the new attractions that are made. And so we have to put right here, so it's energy required to break the bonds, and then this is the energy that is released. Now, if more energy is released than you put into breaking the bonds and the intermolecular forces, then overall you're going to have an exothermic reaction. All right, and so that it would be something that's represented by what's on the screen here. So because these, this release of energy is larger than the input of energy here. And so we have an exothermic reaction. And if more energy is required, then that means that wherever these products are, they're going to be higher than the reactants. So they could be up here, possibly, because here are the reactants. If you put more energy in to break apart the bonds or the intermolecular forces than you released, then what will happen is you will have an endothermic reaction. Okay, easy peasy. So a catalyst, please make sure you understand this. This is massive here. And it's one of those things that they'll just like really quickly just shoot at you and you'll be like, oh, I got this, and you'll say the wrong thing. So don't say the wrong thing. We know what catalysts do. You know what they do. we have on this graph with the black line, that's the uncatalyzed reaction. That's just the regular reaction with no catalyst in it. And then we know we throw in an appropriate catalyst and it reduces the size of the hill, makes the activation energy lower. There we go. By providing some type of alternative pathway, possibly. I mean, there's a couple different options of how catalysts work, but that's irrelevant. But it makes it to where the reaction will proceed faster and it doesn't have to put as much energy in order to make the reaction go. But note that where you start in energy for your reactants and where you end in energy for your products stays the same. That means that this delta H is the same no matter whether it is catalyzed or uncatalyzed. So watch out for that, because they'll like kind of screw around with you with the words. It could be on multiple choice, it could be anywhere, where you just go, oh yeah, the catalyst will change delta H. No, it's not, because the delta H is the products minus the reactants. And if your products and reactants are in the same spot, regardless of whether you have a catalyst or not, then that subtraction, that difference, is going to be the same no matter what. So the delta H stays consistent no matter whether you have the catalyst present or not. All the catalyst does is reduce the amount of energy you have to put in, that activation energy to activate the reaction. That is it. So make sure that you don't get mixed up on that, because it's super important. All right, Maxwell-Boltzmann distribution curve. So we did this earlier in the year. It says here in Unit 3, so it probably sounds about right. When we did Maxwell-Boltzmann, the distribution curves. So pay attention to this, and this is a great review of what we've talked about already with this. And they would ask you which one of these has a higher temperature or which one has a lower temperature. You should easily be able to do this. And you're like, I don't know, what are you talking about? Well, let's take a look at it. So we have our kinetic energy here that's on the x-axis. And then this is like number of particles that are at that particular energy. And what they have done, what this graphic is showing you, is that right here is where the average kinetic energy for all of the particles that are under the curve of the purple graph are right here at 5. And it says arbitrary units, so who knows what the units are, what 5 means, but it's irrelevant. And then under the yellow curve, the average is 10. Now, that's a little bit tricky, because in order to find that average, you see that curve, you're going to have to do some calculus, which we don't do calculus in chemistry, in AP chemistry, or at least not the first year, not in AP. So what you've learned previously is this. Find the peak, right? Here's the peak and of the purple graph. And that means right here, this is where a majority of my particles are at the highest point in this peak. Okay, is it at the average? No, but it's okay. It's at the highest point of the peak. Now go to the yellow graph. Yellow graph, I see highest point of the peak is about right here, maybe? Here. That means most of my particles are here. So if you look at them and you could try and visualize the average, or you could visualize where most of the particles are, whatever works for you in your brain, you're still going to get the same answer either way. But if you take a look at this, you have the purple graph, you have more particles that are at their energy is lower, whereas the yellow graph, you have more particles whose energy is higher. So think about that relationship between kinetic energy and temperature. Remember, they're directly proportional. So that's that sign that looks kind of like that. I'm not the super best at drawing it. But the kinetic energy and temperature are directly proportional to each other. So the one that has the higher temperature is going to be the one with the higher kinetic energy. So in this case, that's the yellow graph, or graph number 2. So this one is at a higher temperature, whereas the purple one has lower kinetic energy. Therefore, it's going to be working at the lowest temperature. Don't forget your kinetic energy is 1/2 mv squared equation. Not really something you will calculate, but just be able to regurgitate that. That is a basic, just sort of science equation that you need to know in life. All right, particle diagrams. And there's something that I want to make sure that you guys understand very, very clearly, and be able to compare. And if they ask you to draw, you could draw, or if they ask you multiple choice, you could pick. So particle diagrams. Number 1, at any one given temperature, let's focus on just this box right here, the 100 degrees Celsius box. Every particle in here doesn't have the exact same velocity. They have an average, so the kinetic energy value that we would get for this particular gas, depending when we have the temperature, we would have to know the mass, and then we would have the velocity. We could calculate the kinetic energy, but it's not, they don't all have the same velocity. They have difference, and it's an average of those velocities, okay? So it's an average. So some are moving faster, some are moving more slowly, and that's okay. And you indicate that by the length of the arrow. So this is like vectors in physics. So you have these with the longer arrows, these guys are moving faster, and then you have some with a really short arrow, and these guys are moving more slowly. And so when you average them together, they have some kinetic energy. Whatever it is, the number doesn't matter. But what you notice, or what you should be able to pick up, is over here on this diagram, notice that I have 6 of identical particles, right? It's the same particles in the same container. All I did was heat it up. So now my temperature is 500 degrees Celsius, and we know our thing, right? If we heat them up, we speed them up. If we heat them up, we speed them up. And if we heat them up and they're at a higher temperature, they have a higher kinetic energy. Well, of course, if the temperature goes up, increase in temperature, that means we increase our kinetic energy. Why? Because we increase our velocity. The mass didn't change. It's still the same 6 particles. We're just heating them up. So the mass stays the same. That's irrelevant. So the velocity has to increase. So notice the length of the arrows on this one are longer. Why? Because they're moving faster. So if you have to read that and interpret it, then you've got it. If you're asked to draw it, you should be able to replicate something like that for them. So remember, not every individual particle has the exact same speed. It's an average of all the particles. Some are faster, some are slower. Most of them are close to that average, but things can happen. Sorry, they bump into something, they could change their direction, all these things that happen that could slow them down for, a second until they get caught back up. So be aware of that. Now, here, great. Don't forget about mass, right? Because we know that the equation is kinetic energy is 1/2 mv squared. So if you're at the same temperature, so if I have all of these noble gases, they happen to be noble gases, which is great. It's a beautiful curve. I love this graph. I love it. It's beautiful. Have all these gases and they're mixed together in a container. They're at the same temperature. If they're at the same temperature, they have the same kinetic energy. All of them have the same kinetic energy. So who's going to move faster and who's going to move more slowly? Okay, well, the big one is going to move more slowly and the small one is going to move more quickly. That should make perfect sense to you, right? And here's a graph that shows particle speed compared to the number of particles that they have. So again, remember, look at the top of the peak. So most of the particles of the solid black line, which are xenon, and if you look at your periodic table, we should see xenon sort of towards the bottom, right, of our noble gases. These guys are the biggest, and they are moving the slowest. Next would be krypton, so his peak is right here, and he's moving a little bit faster, maybe not much, but it doesn't matter. His particles are a little bit smaller in mass, so they're going to move a little bit faster. And then we have argon next, not quite to 500 meters per second. And so argon, who is smaller than krypton and way smaller than xenon, is going to move faster than those two. And then we have neon, and then we have helium. That little dude's moving fast because he's tiny, right? So make sure that you don't forget about mass. The mass doesn't change, so mass stays the same. But the bigger things, if they are at the same temperature, they have the same kinetic energy. So I don't know what temperature this is happening at. Let's say it was at 200 degrees Celsius. Then that means every single one of these gases has the exact same kinetic energy. Who knows how many kilojoules or whatever that kinetic energy is? It is what it is. It's irrelevant. But they're the same. So that means the big ones move slowly and the small ones move quickly. Make sure you know that. Easy peasy though, right? Like we've done this before. Okay, Now heat transfer, and we're almost done actually. When hotter, try that one again. When hotter particles and colder particles, I don't know why I can't say that, are in contact with one another, or they collide or they run into each other, they transfer energy. So they transfer energy from them. Please know that heat transfer, heat exchange, transfer of energy as heat, whatever you want to call it. Okay, know that things go from the hotter particles to the cooler particles, to the cooler one. So it goes from hot to cold. It doesn't go the other way around. It never does. It doesn't happen that way. So you have some particles, the things that are hotter have more energy, right? So you have higher energy and you have lower energy. So heat and energy transfer goes from high to low. And that's the only direction it goes in. It's one direction, from high energy to low energy, from hot to cold. All right, and they're going to do that. And as long as they stay in contact with each other or in the same container or whatever, they're going to do that until they reach thermal equilibrium, until they're the same temperature. All right, so that's important. When two substances are at the same temperature, they have the same kinetic energy. We know that, right? The same kinetic energy if they're the same temperature. We've got that. So make sure you can just sort of get your brain wrapped around that and know the direction that heat transfers, hot to cold. All right, time for 2 questions. We got a 6.2 question and a 6.3 question, and then we're done. All right, so a 6.2 question. We have this reaction. It says draw a reaction path diagram. That's an energy diagram, you guys. Label the products, the reactants, and the delta H. Okay, let's do this. So I've got my energy diagram, also known as a reaction pathway. Be able to know that those are the same thing. I'm taking a look at this. The only indication that they're telling me is I'm looking at my delta H value. This is going to tell me if I'm exo or endo. Look at it, pause, think about it. It's negative, exothermic. So it doesn't matter where you put them, but my reactants are here, my products are here. Please, for the love of all that is good in this world, do not do some crazy looking graph. Make sure it looks like the graphs that we draw. It's got a hump, and then it comes down and levels out. Okay? Don't do anything weird. All right? Don't do weird stuff, because some of you do weird drawings and you need to stop it. This is what they all look like. Now, what they want you to label are the products, the reactants, and the delta H. All right, so these are my products over here, and these are my reactants here. They said to label them, so I don't really know if I'm taking a test if they mean specifically label them or what they're talking about, so I'm going to label them. So my products are N2 plus 6HF plus Cl2. These are my products. They weren't real clear. So if I don't know and exactly what they're asking me for, I'm going to go ahead and put both, okay? Because I don't know what they want me to do. So it's best to cover all your bases. All right, my reactants, I have 2 ClF3s plus 2 NH3s. All right, perfect. So those are my reactants. There they are. Products, reactants, and delta H. All right, so for my delta H, typically what I just do is I draw a dashed line over to where the products are, and then you have an arrow right here, and then there's a lot going on, so I'm going to say delta H is equal to negative 1,196. Notice that it is kilojoules per mole. Gotta put it on there. So that's what they want you to do. That's it. Simple enough. You don't have to do anything else. Done. All right. 50 grams of aluminum with a specific heat capacity of 0.900 joules per gram times degrees Celsius. This is getting into calorimetry, the Q equals MC delta T equation. But we're not doing that in 6.3, so slow down. I know that's scary looking, but don't panic. All right, so this is that C. At 85 degrees Celsius, that's a temperature. We have 50 grams, that's a mass. It's placed into a 100 grams of water, so I have a mass of my water that has its specific heat capacity, which that's another C. there we go, I can barely squeeze it in. And I have another temperature, but the temperature is 25 degrees Celsius. What happens to the temperature, average kinetic energy, and average speed of aluminum? Okay, so they're not asking me to calculate anything. They're asking me what's going on. So this is a qualitative analysis, not quantitative. They want me to qualitatively tell them. It looks like it's going to be a big, ugly math problem. And most of you, or a lot of you, if you're my kids, a lot of you are like, oh yeah, give me the math problem. Let me plug it into the equation and be done with it. But nah, they want you to talk about it instead. So really you're focusing on, you have, let's clear this. You have aluminum and you have water. And aluminum is at 85 degrees Celsius and the water is at 25 degrees Celsius. That's what you need to think about. I've got hot aluminum and cold water. I'm taking the hot aluminum and I'm putting it into the cold water. Got it? Visualize what's happening. So what happens to the temperature, average kinetic energy, and average speed of the aluminum? The aluminum is hot compared to the water, so heat transfers from hot to cold until they reach thermal equilibrium. That means that the temperature for the aluminum is going to go down. Decrease in temperature. I think I was trying to think for a second how I wanted to write it. So aluminum's going to have a decrease in temperature. So if the temperature goes down, what happens to the average kinetic energy of its particles? They also go down because they're directly proportional. So there's a decrease in the kinetic energy of the particles, and then it talks about the average speed of aluminum. Well, if the kinetic energy goes down, think about the equation, right? Kinetic energy equals 1/2 mv squared. The mass of the aluminum didn't change. It's still 50 grams of aluminum. It's just going from hot to cold. When it goes from hot to cold, particles don't just magically disappear or appear. The mass is the same. So get rid of that. If the kinetic energy is decreasing, then that means that the velocity has to be decreasing. And chemistry was really bad about using speed and velocity interchangeably, even though they are different. So I'm going to use the words that they use. So have a decrease in the average speed. They did not ask me to explain, so don't explain if they don't ask you to. Okay, that's big. Some of you are just like chatty Cathy's and you want to talk, stop it. If they don't ask you to explain it, don't explain it, because you're going to say something wrong and they're going to mark it wrong. So be careful. And so that's really it. So let me see, I did pull up this, but I don't really need to go over because we already talked about it. I was going to pull up this problem, but I like the way we did it. We wrote it out. All right, so we are done, my children. Have a great day, and I will talk to you guys later. Bye.